Hello everybody, welcome back. Today we're doing another video. This one's going to be the first of many, which is on structural analysis. And the reason I picked this topic and kind of branched off from strengths materials for a little bit is because the topic is actually really advanced and really takes strengths materials and the concepts we learned there to the next level and applies it to structures that are more realistic in the sense that there's a lot more unique configurations to the way the structure is made. But to start the video, I just wanted to preface it by saying this is going to be the first of many where we cover determinacy and stability to start with. And we're going to be looking into a lot more concepts down the road. So for people who are new to the course, what is structural analysis and why is it important for us to learn? Well, the first thing we need to understand is what a structure is. So first of all, a structure is a system pretty much comprised of connected parts, right? And they use a supporting system in order to support a load applied. And there are many different ways that an engineer can model a structure to analyze this load and how it responds to that load and the deflection it creates because of that loading. And in analysis, that means we need to ensure that this structure is going to meet stiffness and strength requirements when actually constructed. So this sometimes means that we need to do idealized variations of how we're looking at the structure. And we're going to go into detail on what that means later on. But without going into too much detail for now, we can talk about what type of structures we can make. So some of the things that are common in structures are tie rods and beams and columns, which are used in conjunction to make a bunch of structures that we've already seen, like frames and trusses, arches, and things like that. But earlier I mentioned this idea of idealization. What does that mean? Why am I saying we need to idealize the structure? What the heck does that even mean in the first place? Well, we've actually been idealizing structures since we started strengths materials, and we didn't even know it. The point of idealizing a structure is to get the structure in a way so that we can analyze the free body diagram, or so that we can look at the structure in straight line elements, or most importantly in this video, we want to idealize the structure so that it is fixed with a certain support system. That can mean rollers, pin, pin fix, fix free. The possibilities are endless. And these assumptions are based on how loading will actually affect the structure in real life if it was to be constructed. So we're going to recall that our structures could be analyzed using the trusty equilibrium equations that we learned previously, f at x, f at y, and the moment, right? But we do this so that the structure can maintain its equilibrium. And we need to ensure that using those equations. But this equation, or those set of equations, are only important if the structure is statically determinate, which is the whole point of this introduction video. A structure is determinate if all of the forces can be determined strictly using the equilibrium equations, right? If there are more unknown forces, however, in these reactions that are produced by the supporting system, then that means the structure is going to be called indeterminate. Now, why is that important? This is important because the majority of the structures that are going to be analyzed throughout this course and throughout the course of your careers as engineers are going to be indeterminate structures. And this means we need to employ new equations using idealization in order to relate the loading and the deflection to an equation system to solve for those loads outside of the typical equilibrium equations we were using before. Now, the main takeaway from this is that if you have an unstable structure, there is no point to proceed with determinacy because we have already justified the fact that it will not be able to maintain equilibrium and will either rotate or translate based on a given loading. Now, let's take all this information we've learned and apply it to these quick problems here. All right, so now we can hop into the problems. Let's take a look at what the question is actually asking for. We need to classify each of the structures as either statically determinate, statically indeterminate, stable, or unstable. And if it's indeterminate, we need to specify the degree of indeterminacy. So we have all the formulas we need and all the theory to understand what's going on with these problems. So let's look at the first one here. So the first thing we need to do is identify what our reactions are and how many members we have. So we have one member, and we're going to have two reactions, one vertical for each of these roller supports. Now, if we remember one of the first points of indeterminacy, the structure is going to be unstable if we have concurrent reactions. If we notice here, if we draw out where these forces are actually going to be acting, they will be concurrent at a single point. So what does this mean for the structure? This means that the entire structure is unstable. What else did we learn about stability? If we have an unstable structure, then the determinacy is irrelevant because it is not a feasible or constructible structure. Now, for point B, we're going to have to look at what's going on internally within this member because we have three separate members that are joined together by these pins, and then they are resting on rollers with a fixed support at the end. So let's take a look at each of these members individually. Okay, now that we've broken up the structure into its individual members, we can see that we have member 1, member 2, and member 3. If we look to this first member, we have the roller reaction plus the two reactions created at the pin connecting between the two members. So this means that the number of reactions in this member is going to be 3. Now, an important takeaway also from a problem like this is at a pin between members, you're going to have equal and opposite reactions in the adjacent member or the connecting member. So this means that these forces or these reactions are technically known if they were previously solved in this member. So we're going to exclude it from these formulas that we're using above, right? Now for the other reactions that we have not looked into yet, we similarly have a roller and the pin with the two reactions created. Thus we have 3 in this member as well. A similar case where we're going to neglect these reactions in our formulas, and we look at the fixed support, which we know creates a reaction Y, a reaction X, and a moment. So we're going to have 3 reactions. Now using this formula, we can see that we have 3 plus 3 plus 3. So the number of reactions is 9. And we have 3 times 3 members. So we have 9 is equal to 9. Therefore, we can state that the structure is statically determinate. Now we can look at the stability rules. We can see that the forces do not all act parallel in the same members. For example, in this first member, we have an X, we have 2 Y's, thus the parallel clause of reactions acting parallel is not satisfied. And we also don't have a concurrent point where these reactions are pointing towards. Thus, those two are not satisfied. Therefore, we can say that the structure is stable. Now we have the last problem where we're going to do the same thing and we're going to open it up at this pin. Now we have a very similar case with this structure here. We're going to look at this simple member first. We have a fixed end and the pin connecting the two together. So we have 3 reactions here and 2 at the pin. Thus, we're going to be left with 5. We neglect the reactions at the pin in the second member, and we have a similar fixed end here. Thus, we only consider the reactions at this fixed end, so we're going to be left with 3 reactions that are unknown for this member. Now, using a similar formula that we used before, we are going to be looking at a total of 8 reactions because we have 3 plus 5, and we have 3 times the number of members, which is 2. 8 is greater than 6, therefore the structure is indeterminate. And as we recall, we need to figure out what the degree of indeterminacy is. So we're going to take 8 subtracting 6, which is going to equal to 2. I'll just draw it out. Degree of indeterminacy is 2, 8 minus 6. By degree of indeterminacy of 2. However, Is it stable or unstable? Similar things before. There are no parallel and there are no concurrent forces acting within each of these members. So we can justify that the structure is going to be stable. That's pretty much it for this first video. In the next one, we're going to be looking into other types of structures, such as frames and trusses. Thanks for watching.